Amorphous alumina is a high-performance barrier material. It coats metals to prevent corrosion, insulates microelectronics, and seals functional layers in solar cells. The functional performance of this barrier relies on the arrangement of atoms over just a few angstroms, its short-range order, and the precise number of hydrogen impurities trapped inside during synthesis. Mapping this structure is a physical challenge. X-ray diffraction, which requires a repeating lattice to produce discrete Bragg peaks, returns only a featureless signal when applied to amorphous materials. To probe local chemical states, researchers use X-ray photoelectron spectroscopy, or XPS. However, in wide bandgap insulators like alumina, establishing a reliable energy reference to determine absolute binding energies is difficult due to surface charging. Without a crystalline lattice to guide interpretation or a stable reference point, mapping the sub-nanometer architecture of these barrier films requires a different spectroscopic approach. There is a workaround, the Auger parameter. This is an energy difference between a photoelectron and an Auger electron that tracks the local electronic environment while remaining independent of static charging. When amorphous alumina is synthesized via atomic layer deposition, or ALD, the data shows a physical anomaly in this parameter. This chart plots the Auger parameter shift against deposition temperature. A 1-volt shift appears from 25 to 200 degrees Celsius. As temperature increases, the hydrogen to aluminum ratio drops. Why does hydrogen loss drive this significant macroscopic shift? It tracks the evolving sub-nanometer architecture during synthesis. To interpret this signal, we must bridge machine learning molecular dynamics with classical electrostatic modeling of the quantum core hole. An X-ray photon ejects an electron, creating a positive core hole. A higher-level electron instantly fills that void, ejecting the Auger electron. Neighboring ligands then polarize, shifting their electron clouds toward the positive charge. Their arrangement and elemental type explicitly dictate the magnitude of this screening. In wide bandgap insulators like alumina, the aluminum atom lacks a high density of valence electrons to neutralize the core hole internally, making internal relaxation negligible. Because internal relaxation is near zero, the shift in the Auger parameter is a direct measurement of the relaxation provided by the local neighborhood. We must determine if this quantum screening can be modeled using a classical mathematical framework. Using density functional theory, red and blue regions show charge accumulating around a core ionized aluminum atom. The radiograph tracks this screening charge, showing it reaches its maximum within the first nearest neighbor shell. Beyond this shell, polarization drops off, proving screening is a localized phenomenon. This localized behavior clearly justifies using a classical electrostatic model that focuses entirely on the first coordination shell. We use machine learning molecular dynamics simulations to observe how this first neighbor shell changes across ALD temperatures. This grid displays amorphous structures generated by a neural network. At 25 degrees, the network is saturated with hydroxyl groups. Scaling to 200 degrees, thermal energy drives hydrogen out. Pure oxygen replaces hydroxyls, driving a visible shift from violet 6-fold polyhedra to green 5-fold polyhedra. Chemically, a covalently bonded hydroxyl ligand has a lower electronic polarizability volume than a purely ionic oxygen ligand. Replacing these hydroxyls with oxygen structurally alters the electrostatic screening capacity of the local neighborhood around the core hole. The temperature-dependent shift reflects a sub-nanometer phase decomposition. The network moves toward lower coordination pure oxygen polyhedra, changing the extra atomic relaxation energy. We connect these structural simulations to the experimental XPS data using Moretti's electrostatic formulation. This equation calculates the energy shift based on ligand distances, labeled R, and their polarizability volumes, labeled zeta. Extracting the averaged ligand fractions and geometries from the simulations allows us to calculate the expected macroscopic Auger shifts. This chart compares the predicted shifts against the actual lab measurements using Bayesian optimization. The simulated data points cluster along the diagonal parity line alongside the experimental data points. This alignment demonstrates that the classical electrostatic model captures the electronic evolution of the amorphous film across the entire 25 to 200 degree spectrum. Mapping the specific energy distributions reveals the subpopulations of structural environments hidden within the amorphous network. Crystalline references display sharp energy peaks, while the amorphous phases show broad, heterogeneous distributions. These broad distributions represent a variety of individual structural building blocks and the active thermal fluctuations in the glass. Lowering the thermal equilibrium to -263 degrees Celsius in simulation removes thermal noise. Distinct, isolated structural subpeaks then emerge. These results suggest that cryo-XPS could be deployed as a future technique to experimentally isolate and measure these intrinsic structural building blocks. Supported by machine learning potentials and electrostatic theory, the Auger parameter enables a predictive view of the short-range evolution in wide bandgap materials.